Alkali versus alkaline earth. Let's dive into this explainer and unpack the periodic table's most volatile sibling rivalry. So, what actually separates Group 1 from Group 2? Let's break down the chemistry behind their differences. Parked way over on the far left of the periodic table, these highly reactive elements literally demand attention. It all starts here. Group 1 alkali metals rock just one outer electron, while Group 2 holds two. Now you might be wondering, how do those specific electron counts actually dictate their physical size? Well, atomic size increases down the group, but surprisingly shrinks going across from Group 1 to 2. Plus, losing an electron creates a cation. This causes the ionic radius to shrink drastically for both groups. Next up is ionization energy. That's the exact effort needed to literally rip that outer valence electron away. Here's the kicker. Group 1 yields its first electron super easily, but fighting for a second requires massive energy. After losing one electron, Group 1 totally locks down. They achieve an incredibly stable, impenetrable, noble gas configuration. Okay, but what happens when water enters the mix? This triggers a chemical reaction we call hydration. The rule here is absolutely crucial. Hydration energy is always inversely proportional to the cation size. Since Group 2 ions are tinier, they actually release way more hydration energy than Group 1. In reactions, Group 1 forms a +1 state. This makes them much stronger reducing agents than Group 2. Physically, Group 2 elements pack way tighter together. They're much denser than the surprisingly light Group 1 metals. That tighter molecular packing also means Group 2 commands significantly higher melting and boiling points overall. But their coolest visual trait? The insanely vibrant flame colors they produce, from deep red to bright yellow. Now, you'll never find these highly reactive metals free in nature. They're always locked up in combined states. We actually have to extract them from diverse ores deep in the earth, like rock salt or gypsum. So, what happens at the very bottom of Group 1 when that reactivity hits an absolute extreme? You get francium, which destroys itself in 21 minutes. Does extreme reactivity ultimately guarantee a shorter reign?